All right, we're about to dive into a question that sounds like it was pulled straight from science fiction, but it's actually at the very edge of modern math and computer science. Let's get right into it. So, how complex is an idea? I'm not talking about a sentence or a book, but the raw abstract idea itself. Is the concept of a circle fundamentally simpler than the concept of a group in algebra? How would you even start to measure something like that? Well, that's exactly the puzzle we're going to piece together today. Before we can even dream of measuring an abstract idea, we're going to need a ruler. But not just any ruler. We need a way to measure the actual amount of information that's packed into, well, anything. And lucky for us, computer science has already handed us the perfect tool for the job. Okay, let's talk about something called Kolmogorov Complexity. The absolute best way to get your head around this is to think of it as the ultimate zip file. I mean, the most perfect compression possible. It's basically a way of asking, what is the absolute rock-bottom, smallest version of a piece of information you can possibly have? And here's the key insight. The complexity of something isn't about how big it is. No, it's about the size of the shortest possible set of instructions, the tiniest computer program you need to create it. Think of it like a recipe. A short, simple recipe means low complexity. A super long, complicated recipe, that means high complexity. It's that simple. Let's make this real. Look at this simple patterned string here, A, B, A, B, over and over. You could write a tiny little program for that, right? Something like print A, B 7 times. The information is simple, it's got a pattern, so its complexity is really low. Now, compare that to a string of just random garbage. See, there's no pattern to simplify. The shortest recipe you can write is, well, it's just the string itself. That is high Kolmogorov complexity. The information just can't be compressed any further. Okay, so we've got our ruler for measuring information. Awesome. But we want to measure ideas, not just strings of text. And to do that, we have to step into a much more abstract world. It's a field sometimes called the mathematics of mathematics, and it's known as category theory. Now, don't let that name scare you off. Think of it this way. If regular math is all about studying things like numbers and shapes, category theory studies the blueprints that those things are built from. It doesn't really care about the specific numbers, it cares about the structure, like how addition works, or how different systems, even ones that look totally different, share the same deep underlying connections. And this is where it all clicks into place. What happens when you take our amazing ruler for information, our Kolmogorov complexity, and you apply it to these abstract blueprints from category theory? You suddenly get a way to measure the complexity of the systems themselves. You get to measure the idea. So, how in the world do you program an idea? Well, researchers came up with this really cool 3-step process. First, they literally had to invent a brand new programming language, one that could actually describe these abstract blueprints. Then, they used that language to write programs that don't just print text, but that actually build entire mathematical structures from scratch. And the final step brings it all home. The complexity of that idea is just the length of the shortest possible program that can build it. Now, it's one thing to just define something. The real test, the big question, is whether your new definition actually makes any sense. Does this new ruler work consistently? Does it give you good results? Well, the answer turns out to be a huge yes, and it leads to a truly beautiful result. And here it is. This is the payoff. The theorem proves that if two mathematical systems are fundamentally the same thing, just different ways of looking at the exact same underlying blueprint, this method gives them the exact same complexity score. How cool is that? It basically confirms that our ruler isn't getting fooled by surface-level details. It's measuring the true deep-down informational content of the idea itself. This is all really fascinating, but I bet you're asking, so what? Right? Why does it even matter if we can put a complexity score on some abstract math blueprint? Well, this discovery unlocks a much, much bigger picture. See, this isn't really just about math anymore. This is about the very nature of knowledge. Think about a big scientific theory. An axiomatic system, like the basic rules of geometry you learned in school, is really the ultimate form of information compression. You're taking countless observations about how the world works, and you're boiling them down to just a few core principles. This research gives us a formal mathematical way to measure exactly how much compression is going on. The potential here is just, wow. Imagine being able to put a number on the complexity of any abstract thought, or uncovering hidden computational structures inside our biggest scientific theories.
This could lead to totally new ways of organizing knowledge. And it could help us understand the absolute fundamental limits of what we can ever hope to compute or even know.
It is really important to remember, though, that this is the frontier. We're looking at a work in progress in a mind-bending field called algorithmic information theory. The full implications are still being figured out, which honestly just makes it an incredibly exciting space to be watching right now. So, we'll leave you with this final thought to chew on. We started this whole journey by asking how you can measure an idea, but what we ended up finding was a way to think about writing the source code for an idea. And if you can do that, well, that brings up an even bigger question, doesn't it? What are the limits of what we can design, build, and maybe even understand?